In last Wednesday's class, November the 14th, we noted that a traditional and important way to synthesize an alcohol is the acid-catalyzed addition of water to an alkene. We then described in detail two alternative methods to prepare an alcohol. Both of these methods involved a sequence of two reactions. The first reaction was an addition to the CC double bond of an alkene, and the second reaction was, in one case, a reduction, and in the other case, an oxidation. Let me briefly review these alternative routes. The first alternative method is called oxymercuration-demercuration. In this sequence, the first reaction involves the addition of mercury acetate +1 cation acting as an electrophile, with water behaving as a nucleophile to form an organomercury compound. Now, this compound is not isolated, but instead we treat it with sodium borohydride, which is a reducing agent, and in this reduction the mercury is replaced by hydrogen to form an alcohol product. The second alternative method is called hydroboration-oxidation. In this sequence, the first reaction is addition of borane, BH3, to the CC double bond to form an organoborane compound. The compound is not isolated. Instead, it's oxidized with hydrogen peroxide. In this oxidation, the boron is replaced by OH, forming the final product, an alcohol. Now, one thing we learned in our last class is that the oxymercuration-demercuration reaction sequence was different from the acid-catalyzed addition of water to an alkene, in that the direct addition of water reaction mechanistically went through a carbocation intermediate. Because of this, potentially, this reaction can lead to rearrangements, often forming unwanted alcohol products. In contrast, the mercury sequence reaction does not involve rearrangement because no carbocation intermediate is formed in the mechanism. Now, significantly, the hydroboration-oxidation sequence as well does not go through a carbocation intermediate. Hence, rearrangements also do not occur. Let's go through the steps of the mechanism of the boron sequence reaction to show this. Now, in this reaction, the borane approaches the alkene, gets close to it. The boron and hydrogen simultaneously attach to the CC double bond. The reaction, we say, is concerted. Because they basically attach to the alkene carbons at the same time, necessarily the B and the H are adding in a syn fashion from the same side of the double bond. The product, an organoborane, when it undergoes oxidation, it involves a somewhat complicated mechanism, but the overall result is simple. What happens is, in an overall sense, the boron atom gets replaced by an OH group. It's replaced from the same side of the boron. There is no change in the configuration of the carbon when this takes place. The product is an alcohol shown here. Now there's another difference that we'll see when we compare these reactions. Let's use the reaction of 1-propene as an example. 1-propene with the direct addition of water catalyzed by acid, 1-propene undergoing the oxymercuration-demercuration reaction, and then 1-propene undergoing hydroboration-oxidation. In the reaction of 1-propene, this is an unsymmetrical alkene. Both the addition of water reaction and the mercury sequence reactions form the same alcohol. That is, with the OH bonded to the middle carbon. But the boron sequence reaction is different. The alcohol that forms in this case has the OH group bonded to the end carbon, not the middle, as in the previous reactions. Well, let me explain why the boron reaction is different. When the BH bond adds to the alkene, remember that both B and H add at the same time, the concerted reaction. Necessarily they're adding from the same side of the double bond. It's the syn addition. As well now, the boron is the electrophile, hydrogen is the nucleophile. So following the ELNM rule, boron the electrophile bonds to the L carbon, shown here, and hydrogen, the nucleophile, bonds to the M carbon, shown here. This results in the formation of this organoborane product. Note the boron is attached to the CH2, the methylene carbon. Now when oxidation occurs, remember that the boron gets basically replaced by the OH group from the same side as the boron, replacing the boron as it stands without changing the configuration of the carbon. That results in the formation of this alcohol with the OH on the end carbon, the CH2 carbon, not the middle carbon. To summarize important points about the hydroboration-oxidation sequence, the addition of BH to the CC double bond is concerted, and necessarily then a syn addition. Both B and H bond to the alkene carbons basically at the same time, and therefore bonding from the same face of the CC double bond. In the oxidation of organoborane compound, the OH replaces B without any change in the configuration of the carbon. That is, the B is replaced by the OH as it stands from the same side as the boron. Now, let me present you with a problem to solve. The problem is this. We'll take 1-methylcyclopentene as our alkene reactant. We'll take it through the hydroboration-oxidation sequence, reacting at first with BH3, followed by oxidation with hydrogen peroxide in basic medium. What is the structure and configuration of the product? If you want to work this problem on your own, perhaps you might pause the video now and give it a try. All right. Here is a solution to the problem. Remember, when the BH of borane adds to the double bond, it does it in a concerted fashion. Both the B and the H attach basically at the same time or within the same time frame. Necessarily then, the B and the H must approach the double bond from one side of the double bond. In the case of the ring structure here, that means that the BH has to approach the cyclopentene, well, either from the bottom side or the top side. Let's assume that it comes in from the bottom of the ring. So we write in the BH of borane beneath the cyclopentene structure. All right. If the BH is at the bottom of the ring, that means that the hydrogen here is going to bond to the alkene from the bottom. The boron of the BH will as well bond from the bottom. A double bond breaks down to a single bond, and we just write the addition product. The H we show bonding from the bottom with the dash line. Showing that the B bonds from the bottom, we use a dash line to show the new C-B bond. When that happens, of course, the hydrogen attached at the ring here, not shown, and the methyl attached here are both pushed upward. We show that with the bold wedge here for the methyl, the bold wedge for the hydrogen. So this is the correct structure and configuration of the organoborane product. If we wanted to, we could actually isolate this product, put it in a bottle. We don't. What we do is we carry out the oxidation process with hydrogen peroxide in hydroxide medium. Now, the overall reaction here, you can look at it in a very simple way. There's a, as I mentioned before, a kind of a complicated mechanism. We illustrated that in class before. But let's get to the nitty-gritty. Remember that what happens is an OH comes up right next to the B. It simply knocks it off as it stands and replaces it without changing the configuration of that carbon. So take off the B, stick on an OH in place of it without changing anything else, and voila, we have the structure and configuration of our product, our alcohol product. You'll note then that this configuration has the methyl and the OH on opposite sides of the ring. It's a trans product. Now this product resulted from the assumption that the BH attached from the bottom of the ring, but there's a 50-50 chance of the BH attaching from the bottom or from the top. The other 50% of the time it will add from the top. What that will give, haven't shown it here, is basically the enantiomer of the structure that is shown here. So the actual product is a 50-50 mixture of enantiomers. All right. And now I want to discuss a different reaction, still following within the theme of addition to the alkene. In this category that we are going to examine, the reaction is both an addition and an oxidation. The addition that we're going to see will occur in reactions in which two oxygens attach to the alkene carbons. Mechanistically, what we'll see is that one oxygen will behave as an electrophile, the other oxygen will behave as a nucleophile. This new addition reaction is both an oxidation and an addition, and consequently we call it an oxidative addition. Right, the first reaction falling into this category that we're going to look at involves the use of a common oxidizing agent, KMnO4, potassium permanganate. The alkene is treated with KMnO4 in aqueous medium at room temperature in basic media. Now I want to stress that this is being done at room temperature without heating. Now the product that we get involves two OH groups adding to the alkene carbons. A double bond breaks down to a single. One OH group attaches to one carbon. A second OH group attaches to the other carbon. There's an inorganic byproduct that we note. It's called manganese dioxide. It's a dark brown precipitate. Now it turns out as well there's an important stereochemical regularity that we observe. This is illustrated well with this example where we use cyclopentene as our alkene reactant. Cyclopentene reacting with KMnO4 aqueous with hydroxide, and importantly at 25 degrees, that's room temperature. The product that we will get is shown here. The two OH groups, note, are attached to the same side of the ring. It's the cis isomer. This basic product is called a 1,2-diol, or also glycol. The formation of this 1,2-diol is called a hydroxylation reaction. Because the reaction is a syn addition, as we are observing here, it's called a syn hydroxylation. How does this occur? Why is the addition a syn addition of two OH groups? Well, it all starts with the permanganate anion, MnO4-1. It comes up and nestles against the alkene, and what happens is the two oxygens of permanganate will both will bond to the alkene carbons. Now, one of these oxygens, the one here that has double bond character, actually has a partial positive charge. The reason it does is because of the relatively large intense positive charge on the manganese atom. Pulling away electrons puts a partial positive charge on the oxygen. This means that this oxygen here is going to behave as an electrophile. Now in addition, reactions to alkenes, remember, those are basically led by electrophiles. Electrophile is the very first thing that is going to attach to the double bond. And that happens here. The very first thing that attaches is the oxygen bonding here. Now before that bonding is complete, however, there's positive charge that will build up on this carbon. Permanganate at this stage will, in the other oxygen, it's going to develop a partial negative charge. The attraction of opposite charges causes this other oxygen to donate a lone pair to the developing positive charge on the other alkene carbon. That is, this other oxygen is going to behave as a nucleophile. So one oxygen is going to behave as an electrophile. The other oxygen behaves as a nucleophile. Both oxygens attached essentially in the same time frame. Not exactly at the same time, but very close to it. When they attach, therefore, because they're essentially bonding in the same time frame, both oxygens are going to attach from the same side, from the same face of the CC double bond. The product here is a 5-membered ring. Now it's fairly unstable. Under aqueous conditions, with hydroxide ion around. What happens next, a fairly rapid reaction in which this 5-membered ring undergoes a reaction called hydrolysis. In the hydrolysis reaction, the manganese-oxygen bond, each manganese-oxygen bond breaks, a hydrogen attaches to each oxygen, forming this 1,2-diol product. When the MnO bonds break, you're left with a byproduct, MnO2. All right. Now, I want to show you a second reaction that will also result in the formation of a 1,2-diol, and that uses a different reagent. The reagent here is OSO4. That's called osmium tetroxide. This reaction is actually a two-reaction sequence. First, we treat the alkene with osmium tetroxide. An intermediate product is formed. We don't isolate it, but we treat it with a reducing agent, NaHSO3, called sodium hydrogen sulfide. The final product produced is the 1,2-diol. Now this reaction as well involves the syn addition of the two OH groups. Mechanistically, how does this happen? Well, let me illustrate. The first reaction is addition. The osmium tetroxide clamps on to the ring, both oxygens attaching from the same side of the double bond, producing a 5-membered ring. It's called an osmate. The osmate is not isolated. It's treated with reducing agent, NaHSO3, and results in, well, this. In the reduction process, all of the osmium oxide bonds are broken completely. Every bond here breaks, leaving you with pure osmium byproduct. The CO bonds here do not break at all. The process involves in breaking the two oxygen osmium bonds, hydrogens are respectively attached to each oxygen, and you end up with the 1,2-diol. And you can see then that both OHs ending up on the same side of that ring. It's forming the cis isomer. So this other method using the osmium tetroxide is also a syn hydroxylation. Both OH groups bonding to the alkene carbons, attaching in a syn fashion, a syn addition of the two OH groups. Now, this reaction shown here, the addition of osmium tetroxide followed by reduction, is a good reaction. It gives a very good yield of 1,2-diol. But there is some issues. There are some problems. And the problem here is this. The osmium tetroxide reactant used is rather expensive. The osmium byproduct is a hazardous waste material. It's expensive buying the osmium tetroxide reactant, and it's also expensive to dispose of the osmium byproduct waste. Now, chemists have developed an elegant modification of this reaction that we show in the next slide. And this modification, let's look at this reaction right here as being representative. The alkene is mixed with both osmium tetroxide and hydrogen peroxide. In this reaction, hydrogen peroxide behaves as the actual oxidizing agent. The osmium tetroxide is going to play the role of catalyst. Now remember, a catalyst makes the reaction go faster. It's not really consumed by that reaction, so it comes out regenerated, unscathed. Now, this gives us an advantage. We're going to go ahead and use the osmium tetroxide, but we don't need very much. We only need a small amount. It's generally the case with catalysts. You perhaps heard of the phrase catalytic amount. That means catalysts used in small amounts. Moreover, when the reaction occurs, we get our product and it forms in high yield. The osmium tetroxide is not changed, it's regenerated. And so we can actually recover the osmium tetroxide after we've done the reaction. And we can actually recycle it. All right. Let's now move to a different type of reaction. This reaction is a variation of the potassium permanganate oxidative addition reaction that we have previously discussed. In this reaction, we are going to take the alkene, mix it with KMnO4 under basic medium, just as we did before, but one big difference. This time, we're going to heat the reaction mixture, heating it to boiling, vigorously heating it. When we do that, addition will occur, but the addition will be followed by a dramatic chemical change. Namely, what will happen is the whole CC double bond will undergo cleavage to give two cleavage products. The products that we get are shown here. These are carboxylate ions. Carboxylate is the conjugate base of a carboxylic acid. Now, almost always what we do is we don't isolate the carboxylates. If we did, we'd be isolating carboxylate salts. Instead, we do a workup procedure in which we acidify. We add acid, converting each of the carboxylates to carboxylic acids. And carboxylic acids are actually the products or product that we isolate. Now, the actual mechanism of this overall reaction, we call it oxidative cleavage, is rather complicated. But we needn't concern ourselves with this mechanism. Instead, what I want everyone to realize is that this is an important reaction. We want you all to learn it. The product or products that form can be figured out by going through a simple pattern process. It involves a, if you will, on paper, three-step drawing, erasing procedure of organic structures. If you will, as you're going to see, it's as simple as 1, 2, 3. Three-step process. Let's take this alkene shown here to illustrate it. So we have our starting alkene reactant, allowing it to interact with KMnO4 aqueous, with hydroxide, and of course the important process of heating it to boiling. And then of course the product we're going to get, we do an acid workup. We add hydrogen ion. The product or products that we're going to get are carboxylic acids, but what is the structure of those? To figure that out, well, here we go. As I said, it's a three-step writing and erasing process. So to figure this out, you get scratch paper, and get a pencil that has an eraser, or you could use an erasable ballpoint pen. So here we go. What you're going to do then is look at your alkene structure, take your eraser and erase completely that CC double bond. And that's what I've done here. All right. The second step, what we do is doubly bond an oxygen to each of these carbons, the carbons that started out as alkene carbons. So doubly bond an oxygen to each of those, and of course we'll get this. Right? The carbons at this stage are carbonyl carbons. Step 3 involves the following. Look, in each case, look at the carbonyl carbon. Each CH bond that you see, replace each of those hydrogens by an OH group. Each H covalently bonded to a carbonyl group is replaced by an OH group. So for the one on the left, we'll take this hydrogen here, erase it, and write in place of it an OH. The other one, that hydrogen shown here, we'll erase it and replace it by an OH. And we're done. These are the final products that will form. Now here in the next slide we show some other examples of this. If you have this basic alkene structure, erasing the double bond, doubly bond an oxygen, followed by replacement of carbonyl carbon CH, replace the H by OH, you get these two products. In the second reaction, erasing a double bond, doubly bond an oxygen to each carbon, replacing each carbonyl CH by an OH. Well, over on this side, let's see. There's no when you erase a double bond, doubly bond an oxygen, there's no hydrogens attached to the carbonyl, so we'll end up with this ketone structure. On the other side, when we at the end replace each CH by an OH, we'll get well, actually this structure shown down here. Now you note though that that's not this structure is not shown as one of the products. The products that we get actually are carbon dioxide and water. And here's what's going on. Indeed, this is the structure that we will write as one of our carboxylic acid products. But this particular carboxylic acid is carbonic acid. Perhaps you've heard of carbonic acid. It's the acid that naturally occurs in soda pop. One of the chemical characteristics of carbonic acid is that it's unstable and will rapidly break down to CO2 and water. Now, that's really what's going on when you take baking soda and you add vinegar to it. We all know that when you do that, it produces bubbles. The bubbles are carbon dioxide, and really water is being formed as well. So when you acidify sodium bicarbonate, you're actually chemically producing carbonic acid that has a short lifetime that rapidly breaks down to CO2 and water, and the bubbles we see there are the carbon dioxide bubbles. That's why in this reaction I show here, one of the cleavage products is the ketone, the other one, it actually comes out to, in the end, carbon dioxide and water. When you do the reaction, yeah, you're gonna see bubbles. Now, let's move to another instance of oxidative cleavage. In this new reaction, our reactants are alkene and ozone. Ozone has the formula O3. Now, ozone itself is interesting. Ozone is a different allotropic form of the element oxygen. The element oxygen actually exists in three forms. A single oxygen form, the O2 form, that's what we are most familiar with. That's what exists in the ground level of the Earth. And then ozone form, three oxygens bonded together to form an O3 molecule. Now, ozone naturally occurs in the Earth's atmosphere. We find it in the upper atmosphere, the stratosphere. It's a good thing that it's there because it actually protects living things. The so-called ozone mantle, as it's often called, actually filters out harmful UV rays from the sun, protecting living things on Earth. That's a good thing for living things. On the other hand, we also find ozone at the ground level, in the so-called troposphere. It forms as an air pollutant. It's the result of the photooxidation of hydrocarbons put into the air by combustion processes. And that's not a good thing. Ozone at the ground level is actually harmful to living things. It's harmful to lungs. It's also harmful to certain material things. For example, it causes damage to the rubber of tires. Well, you can commercially buy ozone. It's a gas, and it comes in a tank. What you do is basically bubble ozone through the alkene, and when you do, there is a reaction. The reaction is an addition reaction of ozone to the CC double bond. The ozone molecule itself, I don't have the structure written here, but it's 3 oxygens bonded together. The 2 oxygens to the end will basically attach. They're attaching to the same side of the CC double bond, breaking the double bond down to a single, giving this 5-membered ring. Now, this is very unstable, however. This is an intermediate. It rapidly undergoes decomposition. It rapidly fragments. The CC bond breaks, and the 2 fragments reattach to form this product. And this is a relatively stable product. It's called an ozonide. It sits there in your reaction flask. You don't isolate it. What you do is you carry out a second reaction, a reduction reaction. A commonly used reducing agent is zinc in a water medium. Now, the reduction reaction produces, in this particular case, these 2 products. Here, one is a ketone, the other is an aldehyde. Now, I'm not going to go through the actual mechanism of this reduction process. It's somewhat involved, but rather to look at the overall chemical results, starting with the reactants, the alkene and the ozone, and going finally to the products. The structures of these products can actually be predicted by following a similar process that we followed when we did the hot KMNO4 oxidative cleavage reaction. This step 1, step 2, step 3 process. Interestingly, this process that we're going to use here is in fact, well, it's a 2-step process. The 2 steps are the same 2 steps that we employed when we did the steps 1, 2, 3 for that hot KMNO4 reaction. And that's how you can actually come up with the correct structure of the products. Let's summarize this in the next slide. And so here we go. Let's start with this alkene as an example. In the reaction, 2 reaction sequence. First reaction with ozone. The second reaction is the reduction process. To get the final structure of the products, I haven't really shown it, but you can follow along, I think. You get our eraser out and you erase this CC double bond. This gives you 2 fragments. What we do is, as we did before in the hot KMNO4 reaction, we doubly bond an oxygen to each carbon, and that's it. We stop. We don't add anything else. We don't make any other changes. And when we do that, this is what we'll get, and these indeed will be the structures of our 2 products. In our next class, we're going to show you some additional things about this ozonolysis reduction reaction and illustrate how this reaction can be used in the process of elucidating the structure of an alkene, a structure that we don't know. This is in fact an important classical tool for figuring out the structure for an alkene, and you can look forward to that in the next class. Thank you very much for watching the video. If you have any questions, please send me an email. Thank you very much.